Welcome to section 3.9. I tried to get my green screen working today, but as you might be able to see, the green screen is not working super well. But on the plus side, I can like fill this background in with red. Oh, there we go. Give myself red eyes. I don't know. It's not working. But yeah, so we're going to talk about, I'm going to switch this. Don't worry. We're going to talk about the derivatives of logarithmic and exponential functions here. And we're going to start by talking about the derivative of exponential functions. So first things first, there's four things that look similar, but they're not, okay? So this is what we're talking about in this video. B to the x, some number raised to the power that has a variable in it, which is very different than the opposite way. So this is where we can use the power rule. If we want to take the derivative of this, bring down the exponent, subtract 1 from the exponent, and we're good. The power rule does not work for this because it's completely different. This right here, this first thing is a monomial, right? It's a polynomial with only one term, whereas this other thing is an exponential function. They're definitely different. Exponential functions look like this. Monomials usually look like this or like this. So even though they look similar, always keep in mind where the variable is. Power rule is how we do this. And 3.9 is how we're going to do this. Then there's other things that can be confusing as well. Like if you have something like pi to the e, this looks really nasty, but this is just a number, right? Pi is a number, e is a number. So this isn't anything fancy. It is just a single number. Watch out for that. And watch out for this too. You can't use the power rule on this either. You can't use exponential function rules on this either. This is a weird, wacky function. You guys, you want to see what this here? Let's use Desmos and let's talk about some of these things. So b to the x is something like this. This is our exponential function, as opposed to monomials, which are like all of these. All of these are monomials, and this is where we use the power rule. Okay, and then again, pi to the e. That's just a constant. I don't know. Wait, is it really? Oh, it's 22. So it's just this constant function way up here. But x to the x is a real wacky function. We actually will talk about how to take the derivative of this function today. That's for the end of this section. We talk about differentiating this beautiful, beautiful thing. But it's weird and it takes a little finesse. All right. So I just want to start off this whole section again. Just because there's an exponent doesn't mean we can use the power rule. These are all a bunch of different things. Here, we're gonna label this with the triple question mark. All right, and that's how we're gonna start here. So let's move on. And I'll actually mention. We take the derivative of this using something called logarithmic differentiation. That is the last video here. It's a wacky technique, but it's really powerful. In fact, that's going to be the end of chapter 3 is logarithmic differentiation. The end of this entire chapter is logarithmic differentiation. It's very cool. Very powerful. I'm excited. You're going to love it. You're probably not going to love it, but I love it. All right, so let's actually start the material. Sometimes I just get so excited about math. I talk about it forever. It happened to me the other day during student hours, and I was like, no, I don't think the student wants to hear me just rant about other stuff for an hour. I think they want their questions answered. Find the derivative of b to the x, where b is some positive number that's not 0. And you might say, Jason, you didn't tell us what this derivative is. How can you ask us to find this derivative without telling us? Well, student, I have an answer for you. What if I called all of you student? We're going to use something from, remember way back to the beginning of chapter 3. This little guy, the derivative of b to the x is the limit as h goes to 0 of this function evaluated at x plus h minus this function evaluated at x. Is the definition of the derivative, the limit definition of the derivative. You thought you were done with limits? You were wrong. And it's not going to be that bad here. We want to simplify it. So to simplify this, we'd like to do something, because these are similar quantities. But be very careful. We have properties for multiplying and dividing exponentials, but not really any properties for subtracting exponential functions. So what we're going to do is we're going to rewrite the first one a little bit. Limit as h goes to 0, b to the x times b to the h minus b to the x. So these are the same, right? If you multiply two exponential functions with the same base, you just add the exponents, and you can go backwards as well. Well, now we can factor out a b to the x, right? Everything in the top has a b to the x, and we're just left with b to the h minus 1 over h. Now, in terms of h, as h is going to 0, that has nothing to do with b to the x. We can bring our b to the x out front. So all we're left with is b to the x, the original function, times some limit. Now it turns out that this limit is a little complicated. We could look at this graphically and get some approximations as h goes to 0. We could evaluate this limit in Calculus 3 using Taylor series, but for now, we don't really have the tools to evaluate this limit. So, but here's what I want to bring your attention to before I just tell you what this limit is. The derivative of an exponential function is that same exponential function times, this is a number, right? It doesn't matter what x is. If we're looking at an exponential function, our slope is just the function value, b to the x. It's just the exponential function times some constant that has nothing to do with x. All right? And it turns out that that limit is the natural log of b. Okay? So the derivative of an exponential function is itself times a constant. Any exponential function, as long as we want b to be positive, otherwise wacky things happen. And we certainly want b to not be 1. Ooh, sorry. We don't want b to be 1. That was redundant, saying it couldn't be 0. Because if b is 1, we have a very boring function. I'll show you. If b is 1, what does our exponential function look like? That's not very interesting. All right. B being like 2. Whoa, I can't type. B being 2 is more interesting. B being like a half is more interesting. B being negative. We don't want to deal with negative b's. We don't want to deal with this. Okay, so b is going to be positive and it's not going to be 1. And that's how we're going to start. So let's go to theorem 3. I'm going to use the numbering from the book in case you want to find it. Theorem 3.16. And that says for b being positive and b not equal to 1, we have 4 properties. We're only going to start with the first one that we just introduced. The derivative of an exponential function of any base is that same exponential function times a constant. And specifically, that constant is whatever the natural log of the base is. All right. And that's how we're going to start here. Let's do some problems. We'll fill in one more bullet point in this video and then 2 more in the second video. Let's do some examples. Let's start with example 1. Find the derivative of y equals 3 to the x. So we're just going to use what we found in this formula. The derivative of an exponential function is that same exponential function times the natural log of the base. What is our base here? It's 3. So y prime is just that same exponential function times the natural log of the base. And that's all there is to it. Now, of course, things are going to get a little messier. But before they get messier, let's do another one. What about e to the x? So our base here is e. Euler's number, 2.718 ... used for continuous growth. Well, again, we just use the same formula. Jason, this is boring. The derivative of an exponential function is itself times the natural log of the base. Well, in the previous example, this couldn't really do much with this. Natural log of 3 is some messy number, some irrational number, but this is a really nice number. This is e raised to what exponent gives us the inside, which is e. E to the first power gives us e. Right, this is log base e. So the derivative of e to the x is just itself times 1. All right, and that's one of our special formulas. So these top two ones are going to be our main formulas. And then these bottom two ones are going to be special ones that are very common. So let's start with that. This is basically just the same thing as we have above, but a special case. The derivative of e to the x is itself. And you don't have to multiply by a constant. So that is very nice. So if I ask you to take the 50th derivative of e to the x, the first derivative is e to the x, the second derivative is e to the x, the third derivative is the derivative of the second derivative, which is also e to the x, and the fourth derivative is e to the x. You get the idea. It's a nice function. One of the reasons that we like e to the x. Okay, let's get into the messier things. I know y'all have been waiting for this. F of x equals e to the 5x. So really, these just become more convoluted when we start dealing with the chain rule, or the product rule, or the quotient rule, or the inverse function theorem, or trig. We've got a lot of stuff to throw at you now. Let's find the derivative. The derivative of an exponential function is itself times the natural log of the base. Natural log of the base, this is e. So we don't have to worry about that. But we have to use the chain rule here. Take the derivative of the outside function, e, and multiply by the derivative of that inside function. What's the derivative of that inside function? 5. So this is 5e to the 5x. Let's do another one. Y equals e to the tangent of 2x. We can get this much more involved. This one, let's definitely do it off to the side, right? Our inside function, what is inside of our exponential function, is tangent of 2x. What's the derivative of our inside? Here I didn't write it down, but u prime was just 5. What's the derivative of our inside function? Well, derivative of tangent is secant squared. We have to use the chain rule again. Leave the inside the same and multiply by the derivative of that inside. So we got chain rules on top of chain rules. And again, as a reminder for the chain rule, it really can be useful if you write it in this form. U is tangent of 2x, so just do it this way. And then remember that the chain rule says this is going to be dy du times du dx. And this right here is du dx, the derivative of u with respect to x. So the derivative of y with respect to u is itself times the natural log of e. Natural log of e is 1. times du dx, which we have right here, is 2 secant squared of 2x. And all that's left is replacing the u again, and we get our final answer. So y prime is e to the tangent of 2x, put that 2 in front, times secant squared of 2x. That's our answer for part B. I was going to write it right here, but I can't duck my head away this time. I have a solution coming for October in the green screen. I think it'll work. We'll see. It'll come on Monday. I'm recording this on a Thursday. Okay, so that's how we do it. Let's just give you another one. Let's do 2 another ones, actually. What letter am I on? E. Not really following the notes. Y equals e to the x squared divided by x. So you have 2 ways of doing this. You like the quotient rule? You can use the quotient rule. You don't like the quotient rule? Don't use the quotient rule. I don't like the quotient rule. All right, this is y equals x to the negative first times e to the x squared. We can use the power rule. Sorry. Well, the power rule, yes, but also the product rule, right? This is a function of x times another function of x. So we can't just take each derivative individually. We have to use the product rule. All right, so we go off to the side and say, all right, f of x is x to the negative first. F prime of x, use the power rule. It's going to be negative 1 over x squared once you do it all out. G of x is e to the x squared. G prime of x, it's going to take a little bit of work. The derivative of an exponential function is itself, but we have to use the chain rule because there's stuff inside here. Our u, our inside function, our u is x squared. You have to multiply by the derivative of the inside. So g prime is 2x e to the x squared. And now we can use the product rule. Y prime is f prime g plus fg prime. And now just substitute. F prime is negative 1 over x squared times g, which is e to the x squared, plus f, which is x to the negative 1, times g prime, which is 2x e to the x squared. And then we just have to simplify. So we'll have negative e to the x squared over x squared. And then this is 1 over x. 1 over x times x cancels out. And we get plus 2e to the x squared. This is a perfectly good answer. I like this answer. I think it's a useful answer. But usually we write the positive part first. So even though I would take this, I would accept this as your final answer, I'd recommend rewriting it a little bit. 2e to the x squared minus e to the x squared over x squared. Let me just double check that this is indeed the same thing. There's a lot of calculations in this chapter. I need to make sure that when I'm recording these videos, I don't make silly mistakes. It's easier in a class because you guys just raise your hand and say, Jason, I don't understand why that entire function just disappeared. And I say, oh, yeah, I forgot to write it down. It's harder in the video, so keep on letting me know if you see anything. Okay. So you might, if you're checking your answer in the book, they actually also might give it in a different way. The book might multiply that first one by x squared over x squared, so you can combine the fractions. And if you use the quotient rule, you're also going to get this as well. 2x squared e to the x squared over x squared minus e to the x squared over x squared. And then they would combine these fractions and factor out an e to the x squared. So the book could write it in a couple of different ways, but it would be like 2x squared minus 1 over x squared like this, I believe. I didn't make a silly mistake. So you may also see this. Either one of these is perfectly great. And no form, I don't think either one of these forms is particularly simpler than the other. It just depends on what you're doing with it. A lot of times the bottom one is actually a little nicer, but sometimes the top one is nicer too. So, all right, last problem, part F. F is in fun. Nothing new here, just trying to give you guys more practice problems. X times pi to the x. So again, this is a function getting multiplied by another function. Both of these things that are getting multiplied by each other have x's. We are going to have to use the product rule. So just like before, we go off to the side. F of x is x. F prime of x is 1. G of x is pi to the x. The pi makes it look weird. Is this just a number? Is this an exponential function? Is this a monomial, a power function? Or what is going on here? This is a number raised to x. So it's just like 2 to the x or 3 to the x. It is indeed an exponential function. So when you take the derivative, it's going to be the derivative of an exponential function is itself times the natural log of the base. Now we use the product rule. H prime of x is f prime g plus fg prime. F prime is 1 times g, which is pi to the x, plus f, which is x, times g prime, just pi to the x times the natural log of pi. And now we can clean things up a little bit. For example, we don't have to write this 1, and we can factor out a pi over x, a pi to the x. And that'll leave us with a 1 left over in this first term when we factor it out. And when we factor out a pi over x from the second term, we just have x times ln pi. That's going to be our derivative. Let me know if you have any questions. That's it for this video. Tried to give you guys a lot of examples to give you a lot to work with. There's some more examples in the selected homework problems video as well. And then in the next one, we are going to take the derivative of logarithms, which may or may not be better. I'm not sure if it's better or worse. You can let me know. Yeah.